we're now going to look at the ratio test. It has 3 statements. They're all about the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. Let's call that limit L, and L could be less than 1, L could be greater than 1, or L could be equal to 1. If the limit is less than 1, then the series sigma a sub n is absolutely convergent. If the limit is greater than 1 or is infinity, then the series sigma a sub n is divergent. And if the limit is equal to 1, the ratio test is inconclusive, which means use another test. Now I want to point something out. The ratio that we're looking at, a sub n plus 1 over a sub n, these are two series in the same, these are two terms in the same series. And a sub n plus 1 is a later term than a sub n. It matters in what order I set up the ratio, because think of it this way. If I were to set up the ratio a sub n plus 1 over a sub n and get a value of, say, 1/2, then I would conclude the series is absolutely convergent. Everything's fine. But for that same series, if I set this ratio up backwards so that I wrote it as a sub n over a sub n plus 1, I would get an answer of 2 if the original had been 1/2, right? Because now I'm looking at the reciprocal. And then I would think, oh, well, the limit's greater than 1, so it's divergent. I would draw the wrong conclusion. That's one thing. The second thing, note the absolute values. That means if you have an alternating series, then you don't need to include the -1 to the n or the n plus 1 or n minus 1. You just write down the rest of the terms. Terms being a sub n plus 1 and a sub n. Third thing. Folks, for this one, we care if the limit is less than 1 or greater than 1. Now I need to highlight a distinction between this test and another one that we've seen before. Here we see the statement of the limit comparison test. The limit comparison test required sigma a sub n and b sub n to be positive series, or series with positive terms. And we were looking at the ratio a sub n to b sub n. And if that ratio turned out to be positive and finite, then we knew that both series did the same thing. They either both converge or they both diverge. Here's the point I'm making. Number 1, the limit comparison test requires us to be working with positive terms. Number 2, for the limit comparison test, it didn't matter whether the series we were testing or the series we knew was in the numerator or the denominator. We just set up a ratio, and if the result turned out to be a positive finite number, then we were good to go. So it didn't matter if it was 2 or if it was 1/2. And setting it up like in the reverse order, we're just, one way would be 2, one way would be 1/2. In both cases, you'd say positive finite number, you'd be on your way. Number 3, C for the limit comparison test doesn't care if it's less than 1, greater than 1, equal to 1, whatever. As long as the answer isn't 0 or infinity, you're good to go. And if it is 0 or infinity, then it's one of our special cases. For the ratio test, we care if it's less than 1 or greater than 1, and we don't want it to be equal to 1 because that just means that we've used up some time and now we have to use a different test. But notice for part 2 here, if the limit is infinity, I can still draw a conclusion that the series is divergent. Let's look at the proof of the ratio test. And I literally meant look at it. This is out of the textbook. I'm just going to go over this kind of in like an overview, and if you want to read the details, I totally support that. So we see as it starts off, the idea is to compare the given series with a convergent geometric series, and now we have that the limit L by assumption is less than 1. So here I have a horizontal line indicating the limit L, and then a horizontal line indicating the value of 1. Just accept that I intend these to be horizontal lines. We can choose a number r such that r is between L and 1. So here's this number r, I don't care where it is, it's between L and 1. Under the assumption that the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n is equal to L, whatever the ratio is for small n, at some point there exists an uppercase N such that the ratio is essentially closer to L than it is to 1. And in particular, it ends up being between L and R. If you're in that region there, then we have that the absolute value of a sub n plus 1 over a sub n is less than r. Clearing the fraction gives us absolute value of a sub n plus 1 is less than a sub n times r. And going through this process iteratively, we've got that if n is big enough, so bigger than uppercase n, starting with uppercase n plus 1, we have that absolute value of a sub n plus 1 is less than absolute value of a sub n times r, right? Just like the previous inequality we just saw. For a sub n plus 2, you end up with another factor of r. A sub n plus 3 is less than absolute value of a sub n times r cubed. And in general, the absolute value of a sub n plus k is less than or equal to the absolute value of a sub n times r to the k for all k greater than or equal to 1. And that r to the k is functioning as a geometric series. Convergent because r is between 0 and 1. And so the comparison test shows that the series that we're after, starting at n plus 1 and going to infinity, is convergent, which means that the absolute value of this series, or the series of absolute values, is convergent. If, on the other hand, the ratio has a limit of L that's greater than 1 or is infinity, then eventually the terms themselves, the ratio of the terms themselves is greater than 1, and that means the limit is not 0, and so this series would diverge by the test for divergence. I know that was a fast run through, but I'm counting on that if you really would like to understand that very well, you will read it. It's in your book.